In this lecture, we're going to have an overview of Chapter 5. And Chapter 5 is a big chapter. We go through a number of different things that take a bit of time. So I think you can kind of categorize them into the types of chemical reactions that we typically see, and then the calculations that support stoichiometry and stoichiometry itself. So let's start with the types of different reactions. There's lots of these, but I want you to focus on just a few. So the most important ones are going to be double replacement, which I actually think of as precipitation and refer to it as that, precipit. Then we also have reduction and oxidation reactions, or redox reactions. We have acid-base reactions. We have gas-evolving reactions. And combustion. And while there are also single replacement reactions, decomposition reactions, formation reactions, these are the ones we focused on in lecture. And of these, the ones that I think are the most important to focus on for this chapter in particular are these precipitation reactions, redox reactions, and combustion reactions. Acid-base reactions are really important, but we are also going to cover those in Chapter 9. So I strongly recommend trying to be able to recognize them, but know that we'll go into them in more detail. Now, these combustion reactions are actually a type of redox reaction as well. So they're kind of a subset of that. And gas-evolving reactions are typically also a different type of reaction as well. They're either decomposition or replacement or double replacement or redox. And the real trick with them is that they have a product that is gas. Our combustion reactions are always going to have one of our reactants as oxygen. And it'll typically form, if we're looking at just hydrocarbons, it'll produce carbon dioxide and water as gases. Although there are combustion reactions that don't involve carbon at all. So that's not a great rule to follow. It's just the types that we saw the most in this class. Redox reactions really involve the transfer of electrons from one element or molecule to another. And so the way to kind of identify these is that the charge will change on two of your reactants as they become products. And a way to recognize precipitation reactions easily is there will always be a solid form as a product. So a big part of this is going to be recognizing these reactions and being able to look at one and identify it as a precipitation reaction or redox reaction. And so hopefully those little hints are helpful. And I think it's a good idea to go through these reactions and decide what you're looking for each one if you're going to evaluate an unknown reaction to you, to decide what type it is. Now within this, there's a bit more that we do with double replacement and with redox reactions. So let's look at precipitation first, and then we'll look at redox. So within our precipitation reactions, I would like you to be able to predict the products. And that's going to involve exchanging your ions. So if I have AB plus, let's say, CD, the way I would predict my products is I would combine the cation from one of my molecules with the anion of the other, and then I would take the anion of the first one and combine it with the cation of the second. So that way I would then evaluate the products AD and BC. And then I'm going to run to my solubility chart to see if one of these is a product. And if it is, then I have a precipitation reaction. For redox reactions, I would like you to be able to identify the reactant that is oxidized and the reactant that is reduced. And I will not use language like oxidizing agent or reducing agent on the exam. Instead, I'll use oxidized and reduced. And so that oxidized is the one that loses electrons, and reduced is the one that gains electrons. And what you're doing is you're always comparing the reactant to the product for an element and asking, is it gaining electrons as it becomes a product, or is it losing electrons as it becomes a product? If it's losing electrons as it becomes a product, it's oxidized. But the reagent that's being oxidized is always that reactant, not one of the products. And so that's what I'd like you to take away from our types of reactions. And then chapter 5 is very calculation heavy as we introduce stoichiometry. And some of these calculations are kind of fundamental that we can do and manipulate in ways other than a basic stoichiometry problem. And so one of the most important calculations we learn is how to calculate and use molar mass. So molar mass equates 1 mole of a substance to mass in grams. And we typically write it for this, mystery element here, X grams per mole. And this is really a conversion factor that we can use that allows us to convert between the mass of a substance and the number of molecules of that substance. And since chemical reactions depend on the number of molecules colliding with each other, not the mass of them, it allows us to make predictions of how many products will form. And we can use molar mass in a lot of different type of calculations. We'll use it in stoichiometry for sure, but we also can use it in paired with Avogadro's number to convert between mass and a counting number, either the total number of atoms I have or the total number of molecules that I have in a reaction. And Avogadro's number is 6.02 times 10 to the 23rd anything per mole. It's just the definition of what a mole is. So it could be eggs per mole, atoms per mole, molecules per mole. We'll typically use it as atoms or molecules per mole. And so I can take the mass of, let's say, a pile of carbon, convert it into the number of moles I have using its molar mass. And then I can use Avogadro's number to convert it into the number of carbon atoms I have and calculate that actual number. So Avogadro's number is a constant. And you'll have it on your quick reference sheet. You don't need to memorize it. And molar mass is something that you need to calculate from the periodic table. And you do that by adding up the atom's atomic mass for any molecule. All right, the other kind of basic calculation that is also the foundation of what stoichiometry is the mole-to-mole conversion. And so this is kind of the fundamental thing that allows us to predict the products of a reaction or the amount of reactants that participated in a reaction if we know the products. And what it's doing is it uses the coefficients of a balanced reaction to convert between the moles of one substance and the moles of another. And so it allows us to know a very small bit of information, but given a balanced chemical reaction, we can learn about all the other reactants and products within that reaction. And so it'll always be the coefficients that act as your conversion factor. So if I have something like 3A plus 2B forms 1C, my conversion factor to convert between the amount of A and C I have is 3 moles of A equals 1 mole of C, and I can then use that to convert between A and C if I have units of moles. So stoichiometry is going to be a way of predicting products or reactants, as I said, and it follows the same kind of pattern each time. And so here's just the steps for it. One, you have to make sure you have a balanced chemical reaction. And that balanced chemical reaction really means that we have the same number of atoms on both the reactant and the product side. And we balance it by manipulating the coefficients in front of those molecules. All right, two, you're going to, if given a mass, the other name for stoichiometry is actually mass to mass conversions. So we'll convert the mass that's given into moles. And so if I'm going to just use this, 3A, sorry. I'm going to use this 3A plus 2B goes to 1C. So if I'm given like 1.0 grams of A, I'm going to convert that using molar mass into moles of A. And that's going to be using dimensional analysis to set up our conversions. That'll be my molar mass of A, where I have mole units on the top, and the mass in grams of A. The next step will always be to convert between the moles that I'm given and the moles that I'm asked about. So let's say I'm focused on C, I'm trying to predict the products. Then I would take my moles of A and convert into units of moles of C, my product. And so that's going to be that coefficient of 1 for C and 3 for A. And then lastly, I'm going to convert those moles of C, or whatever I need, into mass. And so that would be multiplying it by the molar mass of C to get the mass in grams of my product C. And that's our basic set of steps for stoichiometry problems in general. And they can get more complicated and they can get simpler. If we're given the mass of 2 of our reactants, then we have a limiting reactant problem. And we have to then find out which of these reactants do we have the least amount of. And we can't directly compare their masses because they have different molar masses. And we can't directly compare their moles typically because they'll have a different mole ratio that's used to form the product. And so one simple way, or it's not simple, but it's one kind of direct way of doing this, is just to perform the stoichiometry calculation as if your reactant A reacts completely, and then perform the same calculation, except assuming that reactant B reacts completely, and then use those 2 product values to compare, and whichever one is smaller, that's the amount that will form, and whichever reactant led to the formation of that mass of product, that's your limiting reactant. And so typically those limiting reactant problems are longer, but you're just repeating a stoichiometry calculation again and comparing. And that's chapter 5. It's a big one. Some of the main skills that you need to practice a lot, I believe, to be successful in this chapter is balancing reactions. and doing molar mass conversions.